That'll work.
Yeah, that'll be fine.
Well, it's just about time. It's about time, isn't it? Well, let's see if we have any customers here. No customers so far. Uh, Oh. Well, good morning, students. Let's see if we've got any students here. Not yet. Nobody showed up yet. Well, we still have 9 minutes. So we're waiting for some students to show up here for our thermo class. Topics today are the refrigeration cycle and the Otto cycle. We'll see what we can do with those two. We could put our units in there. This is all metric units. So that would be kilopascals. Kilometers per kilogram. Should we use Kelvin or Celsius? Yeah, I think the book uses Celsius, so we'll do Celsius. Okay, well, let's see. Let's see if I've got any students yet. Not yet. All right. We've got 10. No, we've got 6 minutes. This is in your book. This is refrigeration cycle. It's in your book. It's on starts on page 279. But this example is on 281. So we could put that on the board, I guess. This is R134A, isn't it? It's R134A. This is on page 281. and we're going to go through it. The refrigeration cycle has a compressor from 1 to 2, a condenser from 2 to 3. From 2 to 3 is the condenser. 3 to 4 is the expansion valve, which is a throttling process. And 4 to 1 is the evaporator. The evaporator is where it's at. That's what you bought it for. That's the reason why you have your refrigeration cycle, because evaporator, it cools things off. Go swimming sometime and get out of the pool with a good breeze blowing and you'll cool off, won't you? The reason why you cool off is the water on your skin is evaporating. Hey, Paul, do I need that other light on?
It might help, yeah.
We could try and see. Hey, I've got a student that just showed up.
All right.
All right.
Now you're unplugged.
Stuart, unmute and say hi.
Hello.
Hi. How was your evening? Did you get some sleep?
Some.
Not enough? Are you taking any other courses now, or is this it?
I'm taking strength of materials as well.
Oh my. Online?
Yes.
Oh boy. Well, you're a busy guy then. Well, I believe there's an exam in this class here. Are you aware of that?
Yes.
I believe you got plenty of time to do it, but you probably have to get started here later. Well, Stuart, it's right now, it's just you and me. The others haven't showed up yet, but they still have 2 minutes. Did you have any questions for me?
Is the exam up yet? Because I'm not seeing it.
I think it said 8:30 today.
Okay.
Yeah, in 2 minutes it should be up. But I think you have plenty of time to work on it. Well, our topics for today are this refrigeration cycle. I thought we'd do this example 9.6. It's on page 281. Stuart, can you read that 281?
Yes.
Good. Excellent. Trying to pull this thing up here. There. And so you can read that 281 right there. Yeah. Okay. Hey, we got another customer, Spencer. My faithful student Spencer is with us. Unmute and say hello.
Hello, good morning.
Hey, good morning. Well, I've got 8:30 and even if nobody showed up, I would go ahead with my lecture. Because I get paid whether you guys show up or not. So what we're going to do is go through this example 9.6. Now they did not draw the TS diagram or the PV diagram. Shame on them. But maybe we can do a PV diagram if I can make some room. Gosh, there's some glare right there. I wonder where, I don't know where that glare is coming from, but we'll live with it somehow. Well, I was mentioning this is the compressor from 1 to 2, and this from 2 to 3 is your condenser. From 3 to 4 is your expansion valve. And from 4 to 1 is your evaporator. Now you have all 4 of those in your car. And your car uses R134A. So this is sort of a description of your car air conditioner. But they did not have a property table with the energy transfers. They did not do that. So, and they did not do the TS diagram. So let's do it. It'll be good for us. Now we're lucky because state 1 is exactly on that line. Now that line is called, it's got a name. You see this line right here? That line has got a name. It's called, oh, we got more customers here. We have Parker and Cameron and Bear. Good going. Welcome. I'm always picking on Stuart. Stuart, I bet you know the name of that line. What is the name of that line, Stuart?
Is it saturated vapor?
That's it. Good going. It's saturated vapor. And see, you can just look up the properties at state 1. It's real easy. See, this is real easy. Go to the back and find R134A with me. There it is. And look up, well, no, wait a minute. I don't know anything. Let me read the, what it says here. I'm on page 281. And it says here R134A, and you're at minus 20 Celsius. Well, why don't I write that? See, this is minus 20 Celsius. Okay, now we'll go to table 134A. Paul, what do you think about this little glare right there? What the heck is that?
Is it this? Move.
Yeah, that's what that is. Yeah, that's a little better. Now there's sort of a glare up there. Yeah, maybe we can live with that. Yeah, that's perfect. Let's live with that. That's good. Okay, now what was I doing? Oh yeah, go to 134A and look up minus 20. And it says here, pressure is 133.7. Well, let me write that down. 133.7. Okay, and what is the specific volume? Well, let me read that. Minus 20. Did I get that right? Yeah. 0.14649. 0.14649. See how easy this is? Temperature, well, we already know that. That's minus 20 degrees Celsius. Okay. Specific enthalpy, we'll just read it. It's 386.08. Now you guys better check me on this. Make sure I got those numbers right. Specific entropy minus 20, it says here 1.7395. 1.7395. Oh, I forgot to tell you what these processes are. See, 1 to 2 is a isentrope. Well, it's an adiabat. It's a reversible adiabat. 2 to 3 is isobar. 3 to 4 is an isenthalp, constant enthalpy. 4 to 1 is an isobar. So what we have is an isentrope. Yeah, I'll write these down for you. Isentrope from 1 to 2. Isobar from 2 to 3. Isenthalp from 3 to 4. And another isobar from 4 to 1. That's what you have with a refrigeration cycle. Okay, so what do I put here for the heat transfer from 1 to 2 on this isentrope? Well, it's an adiabat, so you put a 0 there. What about the work per mass? Well, it's a compressor. I don't know what the work per mass is, but it's going to be negative. Hey, have I ever told you that compression is negative work? Yeah, I've told you that. Let me tell you again. Compression's negative work. So from 1 to 2, we're going to get a negative, but I don't know the answer yet. Any questions so far on any of that we just filled in? Okay. Well, let's go to state 2. What do we know at state 2? Well, I don't know. Let me read the problem here. It says the condenser is 40. Okay. Well, let me write that down. The condenser is 40. What they're talking about is right here. That's 40. °C. So state 3 is 40. Let's put it in here. Okay. Now here's a beautiful thing. State 3 is right smack dab on this line. Now that line's got a name. We'll go to my friend Spencer. Spencer.
Yes, sir.
Trying to get something off of there we go. Spencer, what's the name of this line right here? This one that goes this way. Spencer, what is it?
Saturated liquid.
You got it. Good going. A saturated liquid. And see, if you got 40 degrees, well, we could just look it up. Go to the tables again. By the way, I'm on table B.5. And I'm going to go to saturated liquid, and I'm going to write down the pressure, 40 degrees. Here we go. that says 1017.0. Okay. 1017.0. 1017. Don't have room for the 0.0. Okay, I got the pressure. Wait a minute, that's the wrong place. Auga. No, I want 3 as 1017. 1017. But now wait a minute. We said this was a isobar, so this would have the same pressure, wouldn't it? 1017. So we're coming along. We got that. Now let's get the specific volume there. Now my friend Spencer told me the name of that line. Spencer, I forgot already. What's the name of this line again?
The saturated liquid.
That's it. It's saturated liquid. So I can get the V there from the table. Let me find it here. Let's see. We need 40 degrees. Saturated liquid. 0.000873. 0.00873. And we can get the specific enthalpy. That's easy to do. You just go to 40 and it's 256.54. 256.54. Okay. And we can get the specific entropy too. It's 1.1909. 1.1909. Okay. Any question on any of that? I'm on table B.5. That's where I'm getting this stuff. If you don't know what I did, speak up. Okay, well, if you're happy, then what do we got here at state 4? Now, what do we know at state 4? Well, this is from 4 to 1's an isobar, so it'll have the same pressure as well. Hey, you know what? This is going to have the 133.7, isn't it? There you go. So we got the pressure. What about the temperature? Well, you know what? Inside the vapor dome, the temperature stays the same, doesn't it? So it's minus 20. Now, what about the don't know what the V is or the H. Oh, yes, we do. We can figure what the H is at state 4. I doubt if you guys can do this, but I'm going to ask somebody. We'll just see. You guys are pretty smart. You're smarter than I expected. Parker, what's the specific enthalpy at state 4, Parker? Now I'm expecting Parker to say, "Gee, I don't know." That's what I'm expecting. But let's give him a shot. Parker, what do you think? Specific enthalpy at state 4. I really don't expect you to get this, Parker, but surprise me.
Would it be the same as in state 3?
Parker, you are a smart student. How did you know that?
Because 3 to 4 is an isenthalp.
3 to 4 is not an isentrope. Say it right, Parker. 3 to 4 is what?
Isenthal.
There you go. But he knew. He said the wrong word, but he knew, didn't he? See, 3 to 4, another name for 3 to 4 is throttling. It's like a throttle, only they don't call it a throttle. They call it well, you could read the problem. They call it an expansion valve. See, this is what went out. I can't remember whether it was my Toyota. Yeah, I think it was a Toyota. My expansion valve went out, and they wanted $300 and something. And it doesn't have any moving parts. It's very simple. It's just that to get to it, they had to take everything apart, and the labor plus the part, which wasn't very much, but the labor cost a lot, and so I didn't do it. I was too cheap. I rode around all summer with no air conditioning, and I used my 460 air conditioner. The joke is 460 air conditioner, you roll down 4 windows and drive 60 miles an hour. That's a 460. And that's what I did that summer. I'll never do it again. But good going, Parker. Okay, now let's see here. I tell you what, we could get the little s and the little v here at 4. Why don't we do that? Now the way to do that is the little h is equal to hf plus the quality at 4 hfg. And see, we know the h at 4. It's 256.54. And we'll just look these up. And go to your table again and help me find HF at minus 20. All right, I'm looking here, minus 20, HF. It's 173.74. And HFG at minus 20 is 212.34. All right, we're going to pause for a minute and a half if necessary. And I want you to find the quality at state 4. I will be quiet, and I want you to do that, please. Let me take roll here. Not that your grade depends on it, but I just like to know who's who's with me and who isn't here. Today is the 8th. And let's see who we got here. We have Spencer Parker Cameron. Spencer Parker Cameron. Bear Aubrey. Who else we have here? Let's see. Oh yeah, we got Stuart. Well, that's a pretty good crowd. Okay, let's see if we'll go to my friend Cameron. Cameron, unmuted. What'd you get for the equality at state 4? Earth calling Cameron, come in,
I'm still
Cameron.
working it out. I keep messing up the answer.
Hey, that's okay. Don't feel like the Lone Ranger. Let me pick on, I think is Bear with us? Yeah, Bear, what'd you get?
After working out, I got 0.389.
That's what I got.
That's what I got.
Yay!
Cool.
0.3. I got 0.3899. Now, see, with that, we can get the specific entropy and the specific volume. So that's what we're going to do now. The specific volume is going to be VF. You can look it up, see, plus equality at 4, VFG. And the specific entropy is SF plus the quality of 4, SFG. I'll give you guys another minute and a half. and let's get those, shall we? Go for it. Here, I'll write the numbers out for this one. And if I can find those. Okay. We're at minus 20. Four, 5, 7, 6. Okay. Well, I got an answer. I got an answer here for the specific volume of 0.05757. I also got an answer here, but I'm going to wait. I'll give you guys another minute, and I want to see if you can get the specific entropy at state 4 for me. I think I know the answer. I might be rushing you a little bit, but any of you out there have the specific entropy for state 4? Anybody?
I got 1.2277.
That's what I got. I got 1.2278, but we're not going to fight over it. Was that Stuart that just answered me?
Yes.
Thank you, Stuart. Yeah, we're in agreement. Somebody rounded something off there. Well, we're doing great. We're going to fill this in here next. The topic for today, for right now, is the refrigeration cycle. Later, we're going to do the Otto cycle. But right now, we're doing a refrigeration cycle. It has 4 processes, and it goes around and around in a cycle. But we're not through filling in this table of property values and energy transfers. But now let me think now. There might be another 0 in this column here. There is. There's another, where does the other 0 go? It goes right here. Now why is that 0? Because see, 3 to 4 is a throttle, and throttles don't have any heat transfer. No heat transfer. Now, a couple of these work per mass, a couple of these are 0. Let's see if I can call on one of my wonderful students here. I'm going to call on Cameron. I don't think I've picked on you today. I don't remember. Cameron, take a wild guess, Cameron. Two of these little W's are 0, Cameron. Which one do you think they are? See, this is worth a point or two on your test. Yeah, and boy, these are easy to get. What do you think, Cameron?
Would it be 1 and 3?
Let's see, 1 and 3. Nope. See, going from 1 to 2 is a compressor, and compressors require work input. They don't run very good if you don't input well, it's a power input. See, power is work per time. But you tried. No, it's these others, 2 to 3. And 4 to 1. Now the question is, I'm still with Cameron now. Cameron, 2 to 3 is a condenser. Condensers don't do any work. They just condense. Cameron, what is 4 to 1? That's a process, but what kind of process? What's the name of that process, Cameron, from 4 to 1? What's the name of it?
An isobar.
Yeah, it's an isobar, you're right. And see, this is a turbine, this is a condenser, this is an expansion valve, but what is the device, Cameron, from 4 to 1? What is the device from 4 to 1?
I guess I missed that.
That's okay, that's why I'm asking. If you missed it, you're probably not the only one. It's an evaporator. The evaporator is the heart and soul of a refrigerator because that's what makes things cold. Remember when you go swimming and you get out of the pool and the wind hits you and it evaporates the water on you and you get cooled off? Cameron, has that ever happened to you?
Yeah.
Well, that's what happens in the refrigerator. The evaporator cools off the milk and the hot dogs and so forth. It's the evaporator, but the evaporator doesn't do any work. It just evaporates. Pour some water on this sidewalk on a hot sunny day and come back in about 5 minutes and you'll notice that the water has evaporated. Now, how much work was done? There was no work done. You just poured some water on the sidewalk. It evaporated. There's no work done in the evaporator. Okay, well, good. We made a little progress there. Excellent. Hey, let's see if we can get any of these. Now, what do we know about state 2? Now, let's see. State 1 was saturated vapor. Here, I'll write it. Saturated vapor. State 3, one of my excellent students told me what that was. I forget who it was now, but they said it's saturated liquid. State 4 is called saturated mixture. But what is state 2? Let me go to somebody, and we're going to ask them what state 2 is. Aubrey. Hi, Aubrey. Unmute and tell everyone what state 2 is. See, state 1 is saturated vapor. Aubrey, what's state 2?
Is it superheated vapor?
Yay, good going. It's superheated vapor. So, good going, Aubrey. Here, we could write that. Let's see, we got room here. Superheated vapor. There we go. So what you do is you have to go to the superheated vapor table. All right, let's go shopping. We need the superheated vapor table. And the only thing we got on here is the pressure, but I'm going to go to the superheated vapor table. I'm looking here. Superheated vapor. Okay, well, I found one, but I got a problem. They don't have a 1017. They have a 1000 and a 1200, but there's no 1017. Uh-oh. We might have to interpolate. But there's something else that we know at state 2. What else do we know at state 2? We know something. See, from 1 to 2 is an isentrope. So we know something at state 2. What do we know? Here, let me go to one of my wonderful students here. Okay. But back to Stuart. I'm always picking on Stuart. Stuart, from 1 to 2 is an isentrope. The specific entropy at 1 was 1.7395. So what's the specific entropy at 2, Stuart?
Is it also 1.7395?
You got it. I need to get a different pencil here. This thing is starting to get kind of puny. Let me find another one. Yeah, that's one of the dirty little secrets of the refrigeration cycle. This is, oh, that's more like it, 1.7395. I feel better about that. Hey, we know 2 things now. We know the pressure, and we know the specific entropy, but we don't know these. But we have our ways. We can do this. We're going to have to interpolate to do it. In fact, we're going to have to double interpolate. Because see, we don't have 1017. Let me show you what we do have. Let me erase all this stuff. This was a lot of fun there. I tell you what we do have. We do have 1,000 kilopascals. Table B.5.2. And we do have 1,000 kilopascals. And see, what we want is 1.7395. Well, they don't have 1.7395 either. But here's what they do have. We don't need the U. But here I'm going to write down what they do have. And they also have it at 50 degrees. But see, what we want is 1.7395. Well, 1.7395 is in between 1.71 something and 1.74 something. So we could interpolate, couldn't we? We could. But then what we would have what we needed at 1,000 kilopascals. Well, that's not what we got. We got 1017. So here's what you'll have to do. You'll have to go to the 1,200 kilopascals. Now, this is ugly and unfortunate, but life is hard sometimes. sometimes things come along and just mess up our lives like this one here. And what we want is 1.7395. Well, I'll tell you what they have. They have 1.7237. And this is for, these numbers are all in the back in table B5.2. I'm sorry that this is so ugly, but 0.01724, and this is at 50. And then at 60, we have 0.01844, 41608. Wrong number. I wrote down the U. You need the H. 43821 and 1.7584. Okay, guys, what we want is 1.7395. See, that's in between 1.72 and 1.75. Can you all see that it would be possible, after about 20 minutes of hard work, to fill in these missing numbers? You could do it, couldn't you? I know you could. But see, we don't want 1,000 and we don't want 1,200. What we want is 1017 kilopascals. So what you'd have to do now, they call this double interpolation. Hi. What you'd have to do now is interpolate these interpolated numbers that you got before and do a double interpolation. And I know you could do it. Let me just give you the answers. I don't want to bore you with that, and we've studied that before. Let's see, do I have these answers? Is a good question. Yeah, here they are. Tell you what, I was too lazy. I didn't get this one, but I got this one. Now these are the answers after you've gone through all this work. I just want to get to the auto cycle today. And except for that box there, which I was too lazy to do, but you could do it, see, because once you got this, and once you got this, you could interpolate between them, between the 1,000 and the 1,200, and you could get that. Doesn't that sound like fun? I'll leave that to you. But I know you could do it. Now let's go ahead and get these values here. Let's get the work per mass and the heat per mass transfer. Before I do though, is there any comment or question from anyone on how I got those numbers so far? You okay with it? Here, I'll ask somebody. And let's go to my friend. And Spencer, are you okay with it? Do you understand how I got those numbers, Spencer?
Yeah, I'm following along. I understand the process. I might do it on
Great.
my own time just to see, but it makes sense so far.
Good deal, Spencer. It's just tedious and no fun at all, but we can do it. Okay, now we're going to use our first law, And we're going to get these values here. Here we go. I'm going to erase all this if you guys are happy. Now we have to decide which first law we're going to use here, because this is an evaporator. That's a compressor. We have different versions of the first law, and this is important. We got to use the right version. Here, let me show you what I mean. We have a first law, and it goes like this. And we have one that goes like this. It's much more complicated. Too lazy to write out the rest of it. But we got to use the right first law. See, these are both first laws. This is the first law, and this is the first law. But we got to use the right one. Now let me find one of my excellent students here. Parker. Parker, you got a 50-50 chance of getting this right, Parker. Which one of these first laws are we going to use to find these missing amounts, Parker? What do you think? You got a 50-50?
The first one.
Parker, don't go to the casino. You just lost your 50 cents or whatever it is that you put in the machine there. These are controlled volumes. See, this is the control mass version of the first law. That's like for a piston cylinder, okay? This is not a piston cylinder deal. This is a compressor. You got mass coming in and you got mass going out. You got to use this version. This is important. You got to know which one of those to use or bad things happen. Okay, this is not the one you use because we don't have a piston cylinder deal. We have control volumes. Well, let's use it on this. Now this is going to be, I'll pick on Parker since I was asking Parker something. Parker, this is 0. How come? Why is that 0, Parker?
Which one's 0?
This term right here is 0. Why is that?
Because it's a steady state.
Yay, good going. Parker's been listening to me. Bless you, Parker. That's 0. It's nothing in this whole thing changes with time. This refrigerator, when you drive to work, it's in your car, and you have it on full blast. And unless you change the setting, nothing changes with time. Unless you turn the knob there and make it colder, it should be steady state while you drive along for a while. That's 0. Now this here, that's not going to be 0. That's your heat transfer rate. That's why you have air conditioners, to transfer that heat energy the heck out of your car so you'll be nice and comfortable. In fact, just divide everything through by m dot. If you'll do that, you can put a little Q here. And I was doing this one, guys, from 1 to 2. Remember, it's the compressor. And That's for the compressor, that's 0. And this will be little w from 1 to 2. And this will be H1 minus H2. Pretty simple when you simplify it. For process 1 to 2, for the compressor, it's steady state. It's adiabatic. Compressors are adiabatic. Hey, we can get the work per mass. It's just H1 minus H2. All right. Well, let me do that. Here we go. Look, we got H1. We got H2. I got an answer. I got negative 42, 32. How about you guys? What does it mean, negative? How come it's negative? Let me ask one of my wonderful students. That's Cameron. Cameron, this work per mass is negative in the compressor. How come, Cameron? Why is it negative? Unmute. Earth calling Cameron. Why is the work per mass negative in process 1 to 2, Cameron? Cameron's on a coffee break. Well, okay, here we'll pick on somebody else. He'll be back. Cameron will be back. Bear, how come the work in the compressor from process 1 to 2 is negative? How come, Bear? Unmute.
Isn't it because it's compressing?
Yay, good going. Because Mr. Griffin has told us over and over again, compressive work is negative. You might want to write that down. Expansion work is positive. Compression work is negative. Good going, Bear. Okay, well, let's go on. Let's do process 2 to 3 then. And I need a little room here. Let me erase that. And what we're going to do now is process 2 to 3. Well, what's that? That's the condenser. Take an ice cold plastic cup of Dr. Pepper with ice in it and put it on the kitchen table. It will condense on the outside and there'll be a ring of water underneath it. That's condensing. That's what we're doing from 2 to 3. Now this is going to be 0 because it's steady state. And when you divide, let's just divide everything by m dot. And you'll just get little q from 2 to 3 minus 0. There's no work. When you put your cup of ice cold Dr. Pepper, you're not doing any work, and it's not doing any work. It's just condensing. And if you divide through by the m dots, by Jove, that's what you have. All right. Now we're going to solve this algebraically, but now watch it, guys. The algebra says you got to switch those. So it'll be H3 minus H2, won't it? Did I do that right? Algebra students? Okay, do that with me. Let's find the heat transfer per mass in the condenser. Here we go. All right, here we go. Well, I got an answer. I hope I did this right. I need you guys to go along with me here and check me, because I can goof up, but I'm coming up with a negative 171.86. And if that's not right, speak up, because you'll be helping all of us get it right. Okay, there's the heat transfer. You know what that is? That's going out. See that negative heat transfer is going out. Here, let me draw it. I like to put my heat transfers in red. There they are. There's your Q23. But see this Q here, Q41, that's now wait a minute. Did I do that wrong? Just let me think a second here now. I think I did that wrong. Yeah, I did that wrong. Now I'm getting mixed up. Let me pause and see if I can get this right. I don't want to lie to you. No, I think I did that right. Looks like I did that right. See, what's happening here is you're transferring heat from the environment to your refrigerant, and you're cooling off your hot dogs. And this is transferring heat from your refrigerant to the environment. And you're warming up your environment there. Only this is your hot dogs, and this is just your kitchen. Or in case of your car, this is the interior of your car, and this is the outside air in Oklahoma. You're making Oklahoma hotter. I think we did that right. Now let's do the expansion valve. Well, we're lucky on this. There is no expansion valves, don't do any work. Look at that. There's 3 zeros here. How about that? They don't do any work, and they don't do any heat transfer either. But let's go ahead and get the heat transfer for the evaporator. I need a little room to do that. Yeah, let's make that now. Is there any questions so far? Well, I guess we're okay. All right, we're going to do state 4-to-1 now. Or I mean process 4-to-1. We're going to go from 4-to-1, and it's steady state. And when you divide through by m dot, you'll get a Q. There's no work on evaporators. And you'll have H of 4 minus H1. So we'll put that in our calculator and see what we get here. Let's see, H. Well, now wait a minute, algebra students. You're going to have to do this, aren't you? There you go. Okay, let's do that. Here goes. H1 is 386. And then you have to subtract 256. Did you get a heat transfer of 129.54? It's positive. That means you're transferring heat from the environment to your refrigerant. It's going in. All right, we filled in all our boxes except this one. Remember, I was too lazy to double interpolate to get that, but you guys could do it. Now, I want to add these up because we know that the sum of all the little q's in a cycle, the sum of all the q's has to equal the sum of all the w's in a cycle. That is a form of the first law of thermodynamics. All right, well, let's add these up and see what we get. Here we go. 129.54 minus 171.86. I'm getting a minus 42.32. Now let me add these up. Well, you know what? I'm getting a minus 42.32 when I add those up. Hey, they're the same. Look, the sum of the q's is equal to the sum of the w's in a cycle. Okay, good. Now let's see if we answered their questions. What we have done right now is example 9.6. It's on page 281. Let me see if I can find that. Let's see, 9.6. Yeah, here we go. They wanted the COP and the capacity. And let me see if I can explain that. I need a little room here. There's some room there at the bottom. We can use that. In fact, we could use all this room. Let's just make some room here. They wanted the COP. That stands for coefficient of performance. And this particular book uses a beta, the Greek letter lowercase beta. And all of these things are a quotient of something you desire divided by something that costs you, usually money. Now, what do you desire? In a refrigerator, you desire transferring heat from your hot dogs to the refrigerant. See, there's a heat transfer here too, from the refrigerant to your kitchen, to warm up your kitchen. But did you buy the refrigerator? Did you know refrigerators warm up your kitchen? Did you know that? Well, they do. Sometime take your shoes off, and when you hear a click and a whir on your refrigerator, that's the compressor coming on. And stand right in front of it, and you'll feel warm air blowing on your toes down at the bottom of the refrigerator. It's warming up your kitchen. But that's not what you bought the refrigerator for, to warm up your kitchen. See, there's a heat transfer to your environment, the kitchen. No, what you want is this Q41 here. If you can read my writing, that's supposed to say 41. That's the 129.54. That's why you bought it. Now, what does it cost you? Well, it costs you the 42.32. That's the net work per mass. See, you have to plug in this refrigerator. And the 42.32, these are both kilojoules per kilogram. The units cancel, it's just a ratio. But you can get your beta, your coefficient of performance, and here's what I get. I'm getting 3.06, something like that. Now, if you read this problem, they get an answer, but their answer is, well, no, it's the same as ours. That's the same answer that the book gets if you look on page 281. So we did a good job. We found the coefficient of performance. Now they wanted something else. If you read the problem, they wanted the capacity of the plant and the rate of refrigeration. Well, what they want is it's one of those things where it's kind of hard to know what they're asking for. But the capacity of a ice plant or a refrigeration plant, it's this here. It's the QL dot. That's what they want. They want to know what the heat transfer rate is at the low temperature. See, the low temperature in this case is minus 20 Celsius. Now this is equal to m dot times little q, in this case, little q41. Well, we got little q41. It's sitting right here. We know what that is. If we could only get the mass flow rate, we could find that. But if you read the problem, do they give you the mass flow rate? Yes, they do. Look here. They said in the problem that the mass flow rate is 0.03 kilograms per second. Read the problem. I'm on page 281, and that's the mass flow rate. Okay, well, if you know that, you multiply them. And they have a fancy name for this. It's called heat capacity. Okay, well, let me get it. Let's see what it is. You take 0.03 times the 129, 129.54. 129.4. Okay, I got an answer. I'm getting what they call the heat capacity. I'm getting 3 point, I don't know, we can round it off, 3.89. But I wonder what units that would be. Don't we have to have units on everything? Let me ask one of my wonderful students here. Let's see. We got to have units on this. How about my friend Bear? Bear, I need the units. We did this equation here, and I need what the units are, Bear. Unmute and tell me the units. Uh-oh, Bear might be taking a coffee break. Here, I'll help you guys. We're doing kilograms per second, and we're multiplying by kilojoules per kilogram. Bear, are you with us?
Now I am.
Yeah, good going, Bear. I want to know what the units are on this big QL dot.
Wouldn't that just be kilojoules per second?
Yeah, I like it. Now, Bear, you're absolutely right. It's kilojoules per second, but there's another name for that, Bear. What's the other name for a kilojoule per second?
Kilowatt.
Yay, good going. It's a kilowatt. So we have 3.89 kilowatts. Man, that must not be a kitchen refrigerator. I don't think you need close to 4,000 watts to run a refrigerator. Surely not. I don't think so. This must be, you must be at Brahms or something there, and they're keeping their whole bunch of ice cream cold there at Brahms. There you go. Now let's see, did we answer all their questions? Pretty much. Yeah, I think we answered all their questions. Good deal. Anybody have a comment or question before we go on to new and exciting things? Okay, well, nobody seems to have any comments or questions. All right. I thought I'd mention again, you do have an exam. I forget when it's due, but something like late Friday night, maybe. This is just Wednesday, right? I think the
Friday at
exam-
midnight.
No, I think you better check on that. I
And it
think
says
it's,
Saturday at 12 a.m., which would be
yeah, that's like late Friday night, isn't it?
yeah.
On the class schedule, it says the 13th.
What's today?
The 8th.
8th. I don't think it says the 13th. I just looked at it a little while ago. I
I
think
think
it
he's
says,
talking about the syllabus. Says the 13th. Blackboard
Yeah.
says
go with the black.
midnight of the 11th. So the end of the day on the 10th.
Go with the blackboard. Does that make it real late Friday night?
Yes, it's due by Saturday. Before
Saturday,
Saturday.
when the midnight clock goes bong, bong, bong 12 times, it's over. It's going to be late if you wait. We don't want it to be late.
I have another question about Blackboard.
Yeah.
So all of my grade totals are in there, but I can only see my grades on the first 2 homework assignments, which means I don't get comments on my work. So I have no idea like where I'm getting points counted off or anything like that.
Now who am I talking to?
This is Spencer.
Spencer. Okay, so we've got your grades on everything, Spencer. It's just that you don't know
Right.
what the answers are supposed to be.
Yeah, my running total of points, it shows the full number of points, 236. But I
Yeah.
can only see where about 12 of those points come from.
Okay. I guess what I need to do is I could post some keys to some of this stuff. I think I posted the key to the exam.
Yeah, you've done that for the exams, but I can only see like my grades on the first 2 homework assignments.
And what I try to do when I grade your homework is I try to make a comment and I say, problem 2 is missing something or whatever. Did I do that with you at all, Spencer?
On one of the homework assignments.
Well, I'll try to do better. The
You may
other
have done it
ones-
on the others. Like you may have done it on all the others, but I just can't see them at all.
Oh, dang.
Like I can I can email you a screenshot so you can see what I'm seeing,
Yeah.
but
Oh, gee.
I can see grades for assignment 1, both parts, and assignment 2, and
Uh-huh.
the total for the class, but that's it.
So you don't know what you did
Mine is
wrong.
too.
That's
That's on
correct. I have
mine
no
as
idea
well.
where I went wrong.
Of course, now if you got a 4, you didn't do anything wrong, right?
Right, but I don't know about that for any of the homework assignments past the second one.
You don't know what you got? You
No,
don't
sir.
know you don't know
That's
what your
how it
grade
is.
are. Your grade is.
I know my total overall, but not per assignment.
Oh. Well, that's not good. Oh, gee, well. Well, let me think about that. I'm talking to Stuart, right?
Spencer, but I think Aubrey was saying that it's that way for everybody.
Oh, okay, that's Spencer right now. Well, maybe I can figure out what the heck to do there. See, back in the old days, I'd give you your paper back and it'd be right there. You look at it. I miss the old days, students. I was perfectly happy in the old days. Man, this is all new to me. But I'll think on that. Thank you so much, Spencer, for telling me that. Okay, well, here's what I'd like to do is I'd like to take a 10-minute break, and then we're going to study the Otto cycle. If you guys are happy with this refrigeration cycle, we're going to move on and talk about the Otto cycle next. Go stretch and take a 10-minute break, and we'll be back. We'll be back. this. Let's start on new one. Looks good. I got one to do. My students are not saying okay, yeah. Oranges left, looks like there's, looks like there was. Yeah. Yeah, I'll have an orange. Let's go ahead and do that. Well, it's almost time. Now, some of you guys have your computer or calculators there. I wanted to tell you something kind of interesting about heat capacity from that refrigeration cycle that we just did. But I forget. Can one of you look up on Google there for me, heat capacity? Or look up the topic, ton of refrigeration, because I can't find it in my book. And I wanted to tell you guys this. Can you find one of those topics for me on Google, on your calculator, somebody out there? Look up ton of refrigeration and see if it says anything. Anybody. If we can't find it, that's okay. We'll go on and talk about the Otto cycle here in a minute. But there's just something interesting I wanted to tell you. Anybody out there can help me out on that?
Says it a ton of refrigeration is equivalent to 12,000 BTU per
Good
hour,
go-
I guess.
Good for you. 12,000 BTUs per hour. Is that what it says?
I think so.
Okay, good going. It doesn't do it in kilowatts.
It says or 3.5 kilowatts.
That's what I needed to know. Now on that problem, was that Stuart that just did that, or was that Spencer?
It was Cameron.
Cameron, thank you. I'm gonna give Cameron a thank you point. Appreciate your help there, Cameron. Now, let me explain this, and I find this interesting. We got a heat capacity, we did that, of, on our problem that we did, on our example that we worked out, we got a QL dot. That's the heat transfer at the low temperature from your hot dogs to your ice cream to your refrigerant, which was R134A. We got an answer of 3.89 kilowatts. If you were awake during that early morning session there, that's what we got on example 9.6. Hey, you know what? That's a little bit bigger than 1 ton of refrigeration, isn't it? 3.89 is a little bit bigger than 3.5. In fact, it's 3.89 divided by 3.5. It's around a 1.11 ton unit. They sell air conditioners and freezers and big refrigerators. They sell them in terms of a 1 ton unit, 3 ton unit. I believe I have a 3 ton unit at my house, but I forget. I'm going to write this down that you told me. Let me scribble that down. 1 ton of refrigeration is 3.5 kilowatts. If you go buy yourself an air conditioner, and they say it's a 3 ton unit, they don't mean that it weighs 3 tons, okay? They don't mean that you need a forklift that can lift that unit up and set it down that can handle 3 tons. No, they're talking about heat transfer rate at the low temperature. That's what they're talking about. So I thought you'd like to know that. If you go to Sears and Roebuck, I don't think they're open anymore. Sears and Roebuck are closed, aren't they, at our location? But we do have plenty of air conditioning service in Tulsa. And if they quote you, it's going to cost you so much for this 2 ton unit or whatever, now you know what they're talking about. They're talking about the heat transfer rate at the low temperature. And you can either go with BTUs per hour. So you could divide that by 60 and get BTUs per second. And let me try that. 12,000 divided by, now wait a minute though. Wait a minute, you'd have to divide it by 3,600, wouldn't you? To get it per second. I'm coming up with 3.33 BTUs per second. Is one ton of refrigeration, or 3.5 kilowatts, same thing. Okay, that's what I wanted to tell you. Every once in a while, I like to tell you stuff that maybe you'll encounter out there in the real world. Well, this here we're going to encounter in the real world because the Otto cycle is a model of the gasoline engine. And unless you're riding around in a diesel powered or a hybrid or a solar powered car, most of us drive around in gasoline powered cars. Now, what we're going to do together is problem 1058. I think I gave you some homework, but I didn't give you this one. We'll do this one.
The homework isn't
Yeah.
on Blackboard for tonight. There's
Yeah.
no assignment 3 on Blackboard. So we have
Okay.
no idea what the numbers are for this one.
I didn't give you guys any homework. It doesn't
There
say
was
any.
assignment 2. There was assignment 2 due Monday, and assignment
Yeah.
4 due next week. So
Well, what I have here is I have problem 965. Your homework
yeah,
is
that's assignment 4,
yeah.
and we
nine-
just turned in assignment 2 on Monday.
Yeah. Before that, I had 917, I think. So your homework.
Yeah.
Your homework is. Now, who am I talking to?
This is Spencer. Is the one that's in there supposed to be assignment 3 rather than assignment 4?
It's kind of confusing, Spencer, because they keep repeating. In Unit 1, they have assignment 1, 2, 3. Unit 2, they have assignment 1, 2, 3.
Might
Right.
just be a typo.
Yeah, looking at just this unit, should this one be assignment 3 rather than assignment 4?
I don't know, Spencer. I tell you this.
Assignment 3 is problem 9.17.
I thought that was assignment 2.
I tell you this, Spencer. I got your homework problem 515 and problem 519. I did that, and you did real good on that. But I don't have anything from you from 650 and problem 667. And I don't have anything from Spencer from chapter 7, problem 15.
I submitted that one on Monday.
Good for you. And I don't have anything from you from chapter 9, problem 17.
I submitted one of these on Monday. I'm not sure.
Okay. Well,
There's
I'm going to get busy and start grading homework here tonight. But in fact, looking at my work here, this is true for everybody out there. You're all
yeah, 6.
you're all
57.
empty. It's all empty. 650 and 667.
That one was due on the 1st, last Monday.
Okay. I haven't graded it yet. And then there's 715. And I haven't graded any of yours, and I need to quit being lazy. And there's
715 was
917.
due this Monday.
Okay, 917. When is 917 due?
It's not anywhere on Blackboard.
Okay. Well, here, let me write these down. 650 and 67. We'll get organized here, guys. It'll be all right. And then there's 715, and then there's 917. And I don't-
917 is not listed anywhere.
Oh, really? It's not listed anywhere. Wait Well, dang. Okay, well, I'm going to check on those, but on my list here, those we were supposed to do, and I don't have those for anybody. So do what you can and turn it in, and I'll grade them, and we'll get it sorted out. All right, we're going to talk about AutoCycle now. You might scribble that stuff down because I'd like to have grades on all that from you guys. And now this is, we're going to do problem 1058. So help me find that. Now the AutoCycle, let me find where this is. 1058. Okay, I finally found it there. Now the AutoCycle has 2 isocores. And 2 adiabats. And here, let me draw the cycle for you. Now we're going to go back for a while and do PV diagrams. And the AutoCycle is treated as a control mass, piston cylinder. And you know you have isotherms. Let me find my red pencil here. You know you've got isotherms that go kind of like that. But adiabats are steeper. They kind of go like that. They're steeper. And then you have isocores like that. And then you have another adiabat like that. Those are adiabats, those are isocores. You'll see all this in your book. Let me show you on page, I can show you where that is here, just a minute. See if I can find it here. Page 314. On page, you'll see this on page 314, the AutoCycle. And see what this is this is your compression stroke. That's compression. And what this is the ignition. You have a heat transfer in. You're burning gasoline, actually. That's what makes it hot. And that's ignition. And then 3 to 4 is your power stroke. And see, your piston expands because the gas burns, it gets hot. The gas expands, you've got your power stroke. Now 4 to 1 is a model of your exhaust and your intake. And in a real engine, real gasoline engines are really 4-stroke engines. That's not the right word. They go around twice, and the crankshaft turns around 360 degrees, and then it turns around another 360 degrees, and it has the exhaust and the intake. And then it goes compression, ignition, power stroke, and it's called a 4-cycle engine. But we're modeling this isochore as an exhaust intake. And what really takes place is the crankshaft, the engine goes through a complete 360-degree cycle from 4 to 1. Okay, now let's make our table here. Let's see, we'll have 1 to 2. This will be fun. 3 to 4. 4 to 1. P, V, T, delta U, Q, W. All right, let's read our problem. We're going to do problem 1058. Let me find it. And it says 4-stroke gasoline engine. I kind of mentioned that business about 4 strokes, didn't I? 4-stroke gasoline engine runs at 1800 RPM. With a displacement of 3 liters. What they're talking about there is the volume change from 1 to 2 is equal to 3 liters. If you wanted in cubic meters, it'd be 0.003 cubic meters. There's 1,000 liters in a cubic meter. Now, what we're dealing with is little v. Little v from 1 to 2. I tell you what that would be. That would be little v2 minus little v1. See, if you wanted to know what this was, this will be your mass times, actually, that's the change in volume from 1 to 2. This would be your mass times this would be the change in specific volume from 1 to 2. So you'd have to multiply by mass. That's what they're talking about. Compression ratio of 9. What that is usually they use a little r, and it would be V1 over V2. Since those are isocores, you could write that as V4 over V3. It's the same thing. Can you guys see that? Did that show up on the screen okay, you think? I hope. Let me keep reading. Guys, what I'm doing is I'm reading this problem, 1058, trying to understand what they're asking. They said the inlet is 10 Celsius, 100 kilopascals. I get the feeling that this is a 10 Celsius, 10 degrees Celsius, 100 kilopascals. There we go. And after the combustion, the charge is at 2500 K. What are they talking about after combustion? You could call this combustion rather than ignition if it makes you happy. Combustion. And ooh, that's going to be hot. It's going to be 2500 K. Here, let me draw an isotherm through there. There you go. That's your 2500 K. Hey, let's get this in K, shall we? Instead of confusing ourselves, 10 Celsius would be 283.15 K. And see, at 3, this is 2500 K. Will be consistent. Now let me keep reading now. I'm reading problem 1058. Find the highest cycle pressure, mean effective pressure, blah, 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 blah. Well, that's all the info that we have. Let's see what we can do with it. You got to understand something. We're dealing with air, basically. Now, it's true you've got some gasoline mixed with that air, but it's mostly air. Oh, looky here. We got the pressure and the temperature, and it's air. P1 V1 is equal to RT1. Ideal gas law, it's okay here, it's air. I'm going to be quiet now for a minute and a half, and I need you to tell me what this little v is. If you know what P is, and you know what T is, and you know what R is, now you got a minute and 15 seconds. Go. I'll be quiet, and then I'm going to ask one of you. I want you to get that little v for me. Go for it. But back to that homework that I don't have recorded. Part of that is my fault. I know a bunch of you have turned in homework, and I've just been too lazy to grade it and record it. And I will try to make a note there of what went wrong. And when you get your grade, read the little note. Maybe that'll help. Okay. Stuart, I'm always picking on you. What'd you get for this specific volume, Stuart?
I haven't finished working it out yet.
Take your time. I'm pushing you. I'll have another sip of water here. Take your time. Stuart, do you have it yet? I'll keep bugging you.
I think I missed where we got R.
Oh, well, R is 0.287. It's air. It's the gas constant for air. I want you to memorize that. I don't know if you guys can read that. It's off the board on my monitor here. Let me see if I can move this without screwing everything up and wrecking everything. Yeah, that's a little better. Well, I got the little specific volume. Stuart's still working on it. Well, what about another friend here? How about Spencer? Do you have that yet?
I got 0.813 meters cubed per kilogram.
Yeah, that's what I got. I got 0.8126. Spencer rounded off, but that's okay. All right, well, let's move on then. Okay. We're going to fill in this table. We're going to do this auto cycle. I need this room here, so I'm going to erase all this stuff. Now, here's the dirty little secret of the auto cycle. They gave us the compression ratio. It's called the compression ratio. They said it was, uh-oh, I lost my page. Anybody remember what it was? It was 9, wasn't it? They say 9? Yeah, the compression ratio is 9. Now what that means is little v1 over little v2 is 9. Well, we know little v1, we just figured it out. So we can get little v2, here goes. I'm getting 0.0903. Did that make sense? I hope it did. Okay. Now I've got a small picture of myself right in front of that PV diagram. And I don't know what you guys are looking at. Do you have this PV diagram okay, where you can read it, everybody?
Yeah.
Good, excellent. Okay, now here's the thing. If 2 to 3 is a isochore, then I know what the little specific volume is at 3. It's the same. It's 0903. Now, if I lost anybody, just speak up. And I can also get what the specific volume is at 4, because there's an isochore between 4 and 1. I want to see if you guys know what I'm talking about. How about Parker? Parker, what's the specific volume at 4? Go for it, Parker.
0.8126.
Good going. He's with me. He understands. Now, if you don't understand, just speak up. Okay, well, we got that. Hey, wait a minute. Look here. P3, V3 is equal to R, which we know, it's air. It's 0.287 times T3. Hey, wait a minute. We know what V3 is, and we know what R is. So give me P3. Go ahead. Give me P3, and then I'll call on I think Cameron is next. Cameron, be warned, I'm going to call on you here in a minute. And I'm going to solve for P3. Here I go. Well, I think I have it. Cameron, do you have P3 yet?
No, not yet.
Take your time. I'm pushing you.
I don't think
How
I'm.
did we get?
Go ahead.
How did we get the 0.0903?
Oh, thank you for asking. The compression ratio is 9. That's in the problem, if you read the problem. Let me read it to you.
Okay, I see now. I read that 9 as a Q.
You understand now? Okay, let me
Yes.
keep talking. You do understand. You don't need my help? You got it?
Yep.
Okay, he doesn't need my help. Good going. You just divide by 9. Okay, now back to, I think I'm back to Cameron again. I'm picking on Cameron right now. What is this pressure at state 3, Cameron?
I think I keep doing something wrong.
Well, what are you doing?
I'm
Just
getting
tell
a
me.
very big number.
No, it is a very big number. This pressure goes way the heck up.
So does 7,945 sound right?
It is right.
0.736.
7, 9. Here, I'll round it off. 7,946. I just rounded off, but what you had
Yeah.
is precisely correct.
Okay.
But yeah, when that spark plug ignites that gas, boom, pressure goes way up. Okay, well, good. Now, let's talk about these a minute. On these Qs, do you remember there's 2 adiabats? So 2 of these Qs, little Qs, are going to be 0. You see this adiabat from 1 to 2 and adiabat from 3 to 4. We're going to have zeros on those Qs. Where do I put them? Well, I put one there. See, these will be kilojoules per kilogram. And I'll put one there from 3 to 4. Okay, now on these little W's, there's 2 of those little W's that are going to be 0. Now let me go to my friend Bear. Two of these little W's are going to be zeros. Bear, which ones are they? Where do I put the zeros? Earth calling Bear, come in, Bear. Unmute. Uh-oh. I think we lost Bear temporarily. Aubrey, help me. Aubrey, I need 2 zeros here on this column. Where do I put them, Aubrey?
The second and the fourth column.
Let
the
me
row?
think. Yeah, because see, from 2 to 3 is an isochore. Oops. And from 4 to 1 is an isochore. There's no work. Hey, you don't do any work on an isochore. See, isochores, what that is you don't move, see? to do work, you gotta move. You gotta have displacement. Okay, well, that was fun. We got a lot of empty boxes here. What do we do now? You guys have any ideas? I'm gonna throw it open to you. I'll make some room down here so I can write. But we got some empty boxes to fill in. We have to know how to do it. Any suggestions from anybody? How are we going to fill in some of these boxes? Well, nobody's helping me. Okay, well, I'll help you. How's that? Going from 1 to 2 is an adiabat. Now, this is an ideal Otto cycle. It's an ideal Otto cycle. And what we're pretending is that we have reversible adiabats there. If you have a reversible adiabat, let's review what the second law looks like. The second law, but now wait a minute, we're dealing with control masses here. The second law goes like this. That's the second law. And see if it's an adiabat, this is 0. And if it's reversible, this is 0. If that's 0 and that's 0, guess what this is? It's 0. These are all 0. Everything's 0. And when you have delta S equals 0, they have a special name for that. Does anybody know the name for that when delta S is 0? Here, we'll go to somebody here. I think we're back to Spencer. I'm always picking on Spencer. No, it's Stuart. I'm always picking on Stuart. Stuart, what do they call it when delta S is 0? They call it something.
Who are you asking?
I'm asking, delta S is 0 on these adiabats, on these reversible adiabats. And there's a special name for processes that are reversible and adiabatic. When delta S is 0, they call it They call it
Isentropic.
That's it. That's it. It's isentropic. I don't know if I got room to write that. Here, let me just write it for you here. If delta S is 0, and delta big S, delta little s, same thing, they call it isentropic. Some people pronounce it isentropic, but we're not going to get hung up on the way you pronounce it. It's isentropic process from 1 to 2, and also from 3 to 4. And it's an ideal gas because we're dealing with air, and we have a lovely formula that goes like this. I think I derived this for you guys one day recently. you could go back and watch the lecture. See that lovely formula there? And remember the warning now, it only works for the isentropic ideal gas. It has to be an ideal gas. If you have an isentropic ideal gas, then you have this formula. But wait a minute, there's another part to it that goes like this. I'm sure I showed you guys that. Now, in this case here, we don't have P2. We have P1. You can circle that. K, we can look up for air. That's just in the back. Remember what K is. It's C sub P over C sub V. For air, it happens to be 1.40. We know what T1 is. Oh, we don't know what T2 is. Too bad. But we do know what V1 over V2 is. It's equal to 9, isn't it? See, that's the compression ratio. So we're going to plug in those numbers. Here we go. I'm going to plug those in. Here's our equation. T2 over T1, 283.15. Equals 9 to the 1.4 minus 1. Did I lose anybody? I hope not. Now I want you to solve that for T2. We're going to get T2. Go for it. And I'll call on one of my best students here in just a minute. I'm going to call on one of my best students. Hey, I've got it. I've got what T2 is. I think I called on Stuart the last time. I'm always picking on Stuart. Spencer, have you got the T2 yet on this here, Spencer?
Not quite yet. I just stepped away for a sec, so I just got back.
Oh, that's okay. Let me go to my friend. I'm kind of mixed up here. How about my friend Parker? Parker, do you have T2 for me?
I got 681.88.
Yeah, that's what I got. 681. Here, I'll round it off to 9. There we go. Hey, we just figured out the temperature here at state 2. That's good. I think it goes through there like this. Just a minute here, let's see. Yeah. Here's state 2. We just figured out state 2 is 681.9. See, the temperature at 1 is 283.15. And we're coming right along. Hey, look at here. We know V2 and T2. Look here, guys. P2V2 is equal to RT2. We can get P2. See it? We can get P2 because we know V2 Look at there. We know V2. We know R. And wait a minute, that's supposed to be a T2. And we know T2. We can get P2. Go ahead. Do that for me. And I'll call on one of my students here in just a minute. We're trying to find P2 from the ideal gas law. Cameron, do you have that yet?
Not yet.
Still working on it?
Yes.
Keep working.
$195.7.
I didn't get that. Hey, let me write it out. I could be wrong, but I'm going to write it out. P2, now we know, is, wait, we're getting mixed up here now. No, we don't know P2. But V2 is 0.0903. R is 0.287. And T2 is 681.9.
Does 2167 sound better?
I must have done something horribly wrong. Let me do mine again, Cameron. No, now what did you get?
2,167.
Good for you. That's what I got. If you do this enough times, you're bound to get the right answer. Okay, we did great. We got that. Let's go to state 4 now. And here's the dirty little secret of solving for state 4. If you're all happy. Any comments or questions from anyone on what we've done so far? Okay. All right, well, here, I just need the room to work down here. Okay, here's the plan. Now, from 3 to 4 is an isentrope. Going from 3 to 4, delta S is 0. It's an isentrope. And it's also an ideal gas. And so you can do this equation here. T4 over T3 is equal to V3 over V4 K minus 1. Do you notice how the numbers go big number, little number, big number? They kind of flip. You might want to write that down someplace because they flip. Now we know T3. And we know what this ratio is. I think that ratio is 1/9, isn't it? Yeah, it's 1/9. And we know what K is. K is 1.4. Okay, put that in your calculator. We know all that stuff. Here, I'll circle that. If I circle something, that means we know what it is. I want you to solve that and get T4, and we'll put it right here. Go for it. Well, I got T4. And we're going to go to one of my very best students, Bear. Bear, have you got T4 yet?
Not yet.
Take your time. I'm in no hurry. I'm in no hurry. If you need me to, Bear, I'll write it out. What we're solving for right now is T4, and it's an isotherm that comes zinging here through here like this. And we're going to have it here. If Bear will put in those numbers, we'll get it.
Sir, I can't quite read what the V3 is. What is that
thank
number?
you. Thank you for asking. It's 0.0903. It's the same as V2, 0.0903. Can you read it now?
Yes, sir.
Yeah, or if you're lazy like me, Bear, we know it's 1/9. Remember, the compression ratio was 9, and so when you flip it, it's 1/9. I was just lazy. I just put in 1/9.
I got 1038.16 for.
That's what I got. I got 1,000. I'll just call it 1,038. That's good enough. And here, let me mark that.
Isn't that the temperature, not the pressure?
Oh, thank you so very much. That's a thank you point. Now, who was that? Was that Spencer?
Yes, sir.
Spencer, you get a thank you point. Proud of you. The temperature is 1,038. It was not the pressure, but thanks to Spencer, because he's awake, see? We got to be awake in this class. Spencer got that. He helped me out. We got 1,038. Good going. Let me write it down here. We just figured this is 1,038 Kelvin. Good going. Now we're going to figure out P4. Well, how do you do that? Well, hey, here we go. We can do this. We can do this. We're going to go P4 V4 equals RT4. Yeah. Do we know P4? Well, no, see, that's what we don't know. But we know everything else. Put in the numbers and get P4 for me. I'm going to do it. I want you to do it. Let's see if I can beat you to it. On your mark, get set, go. Well, I've got P4. I've got an answer. What about, let's go to Aubrey. Aubrey, did you get P4?
I got 366.61.
That's what I got. I'm going to be lazy and just go 367, Aubrey. Kilopascals, 367. But I got what you got. I just rounded off. Now, I wonder if those are the answers I got before. Yeah, those are good answers. Yeah, that's good. Well, we filled in all of those. And that's what I got when I did this before. Those are all the same as what I got before. So I'm pretty happy with all that. Okay, well, great. Wait a minute, we haven't done any of these delta U's yet. The change in specific internal energy. We got to do those. Do you guys know how to get those? I was picking on Aubrey. Aubrey, do you remember how to get delta little u? You remember how to do it?
Do we use Q minus W?
Say that again.
I know the first law is delta U is Q minus W,
Yeah.
but I'm not sure what else to do.
Oh, okay. That was good. If we had Aubrey, if we had the little w, we could do it, couldn't we? The trouble is we don't have the little w. Here's what you have to do, Aubrey. Make a little room here. We have to use this. Now we know what C sub V is for air. C sub V for air is 0.717. We could look that up in the back. Let me show you where that is in the back. It's in the tables back there. And it's on page table A.5. You guys could look that up on table A.5. After a while, if you use it often enough, you'll just memorize it. Okay, so if you want the change in specific internal energy from 1 to 2, then you'll need the change in temperature from 1 to 2. Well, it looks like it got hotter, didn't it? It got hotter, so you take the difference times that, and we can get the delta U. Here we go, I'm gonna do it. Now the change in temperature is 681.9 minus 283. Well, here's what I got. Now wait a minute, you got to multiply 0.717. I'm getting 285.9. And I want to hear from my students. I want at least 2 students tell me that that's what they got. I want to hear.
That's what I got.
There's one of them. How about another one?
That's what I got as well.
I'm happy. Good. Okay, now we're going to fill these in. It's the same stuff, guys. It's just that we're going to go delta U from 2 to 3 is equal to 0.717 delta T from 2 to 3. See, there's 2, there's 3. Do that. We're going to get that one. Here we go. We can do this. Well, I'm hoping this is what you get. I'm getting 1303, maybe rounded off to 6. So there's our delta U there. Let's go ahead and get these. It's the same old boring thing, guys. It's just that we're going from 3 to 4 now. But I still would like to hear somebody say, that they got that. Anybody get 1303.6?
That's what I got.
Uh-huh.
Yeah, good going. All right. Here we're going to get 3 to 4 now. All right, I'm going to do it. Okay. Wait a minute, I did that same one over again. I got to do this one here. I did the wrong one. So I'm going to do this one now. Hey, I got a minus. Anybody get a minus 1048? Maybe 0.3? How come it's minus?
Uh-huh.
Hey, there you go. I heard an uh-huh. How come it's the change in specific internal energy is minus going from 3 to 4? I wonder why that is. Why is it negative? Hey, we'll pick on somebody here. I love picking on. I shouldn't love that. Parker, how come the change in what do they call that? Specific internal energy going from 3 to 4 is negative. Why is that, Parker?
Because the final temperature is lower than the initial.
He's got it. You know what? He's got it. He's got it. You're cooling off. You're cooling off. You were really, really hot, 2,500, and now you're 1038. Man, that is a heck of a cool off. Over what? Over 1,000 degrees cooling off. Hey, if you cooled off 1,000 degrees, you're going to have less energy. Did you know energy depends on temperature? And so if you cool off, you get a negative. Okay, well, let's do this one. Here, I'll write this one out for you. Make sure you guys get this. what I'm going to do right now is delta U from 4 to 1. And we're going to take the 283 and we're going to subtract the 1038. And we're going to get the change in specific internal energy from 4 to 1. Okay. You're cooling off again. Look, you're going from 1,000K to 283K. You're cooling off. It's going to be negative. Here we go. Well, I got a negative answer. I'm getting negative 541.2. It's negative because you're cooling off. You lost some specific internal energy. I think you lost it to the environment because see, there's a heat transfer out. Here, let me draw it for you. Right here, there's a heat transfer. I don't know if you can read my writing. It's getting awfully messy. But there's a heat transfer out. There's a heat transfer in here. That's Q23. But wait a minute, there's no heat transfers between 3 and 4 and 1 and 2. The Q's are 0 going from 1 to 2. Look here, from 1 to 2, the Q is 0. And from 3 to 4, the Q is 0. Because those are adiabats. See, an Otto cycle has 2 adiabats and 2 isocores. Okay, well, we got a few more boxes to do. Any comments or questions on any of that until we do those last boxes there? Anybody have a problem with any of that? Okay, well, let's get those. Now, the way you do those is you use the first law. Now, this is a piston cylinder, and the first law is very simple. It's like that. And look here, we know delta U. And hey, look here, we know Q. We should be able to get W. I tell you what, it's either a plus or a minus 285.9. What do you think it is? Is it plus or minus going from 1 to 2? And here, I'll pick on one of my wonderful students. I think we're back to Stuart. Stuart, I'm always picking on you. Stuart, is the work going from 1 to 2 positive or negative? You got a 50-50 chance, Stuart, of getting this right.
Negative.
It's negative. It's negative. You know why it's negative? Because going from 1 to 2 is compression. Have I ever told you before that compressive work is negative and expansion work is positive? Yeah, I've told you that. I've told you that, what, about 6 or 8 times? If you're like me, if you're a normal, it takes about 6 or 8 times for things to finally soak in. It'd be nice if you could hear something once and get it, but most of us need to work on things. Okay. Well, let's do the first law from 2 to 3. Now, going from 2 to 3, It's a little different. When you're going from 2 to 3, you got the Q23 and the little W23. And you know what the little W23 is, it's 0. So we should be able, if we know what that is, we should be able to get that. Now guys, this is either plus or minus 1303.6. Let's go to one of my wonderful students here. Spencer, the heat transfer going from 2 to 3, is it positive or negative, Spencer? What do you think?
Positive.
Absolutely, it's going in. Did you know that heat transfer in is positive? Heat transfer out is negative. So we did good on that. Well, let's do this one. Now this one here, guys, is either going to be plus or minus 1048.3. And let me go to one of my wonderful students here. I think Parker, I think I've been picking on you too many times, but that's okay. You're a good sport. Parker, the work per mass going from 3 to 4, is it positive or negative, Parker? You got a 50-50 chance. Say that again.
Positive.
Positive. You got it. Good. Jolly good, Parker. It's positive. Now here's why. Can you see going from 3 to 4 is expansion? It's expansion. Expansion work is positive. Compressive work is negative, but expansion work is positive. Now let's go to process 4 to 1. Now in process 4 to 1, let me rewrite it here. We're going to write the first law of thermodynamics for control mass, which is what we have. From 4 to 1. All right. Hey, look at here. We know what that is. We don't know what that is, but we know what that is. And so this is going to be plus or minus 541.2 kilojoules per kilogram. And we'll go to my friend, Cameron. Cameron, you have a 50-50 chance of getting this right, Cameron. Were you the one I told not to go to the casino?
No, we'll see how lucky I am, though.
I don't remember. Cameron, the heat transfer, what are we doing? Yeah, the heat transfer from 4 to 1, is it plus or minus, Cameron?
Would it be minus?
Yep, good going, Cameron, you're a winner. Yeah, it's minus. See, the algebra tells you that. Look, if this is minus 541.2, and this is a minus 541.2, and that's a 0. Hey, the algebra works. Now tell you what, let's do. Let's add these babies up and see what we get. Because remember, in a cycle, the sum of the Q's has got to equal the sum of the W's. Well, we're going to add this up and see what happens. Here we go. 1303.6 minus 541.2. I'm getting 762.4. Now let's add these up and see what happens. 1048.3 minus 285.9. I'm getting 762.4. Hey, that's good, guys. Look, in a cycle, the sum of the Q's is equal to the sum of the W's. Yay, that's good. Hey, we filled in the chart. I'm sure they want to know the, what do they call it? The efficiency. Let's find the efficiency. Here we go. Before we do that, any questions or comments from anybody? You're all okay? Well, all right. Okay, we're going to find the efficiency of this cycle here. All right, now the efficiency, they use a Greek letter eta. Kind of looks like that. Kind of looks like an N, really. It's a Greek letter eta. Alpha, beta, gamma, delta, zeta, eta. It's an eta. That's what it is. Is that the sixth letter? Let's see. Alpha, beta, gamma, delta. Wait a minute. Alpha, beta, gamma, delta, epsilon, zeta, eta. I think it's a seventh letter. Anyway, here we go. We're going to get that. Now, efficiency, this is efficiency. It's always what you desire divided by something that costs you. Well, what you desire is this right here. It's a heat engine. It's a power cycle. See, you're getting power out of this thing. And so in the numerator, you got 762.4. Now, what is the cost? Well, you got to pay for this 1303.6. See, this here, you don't pay for that. That's just heat transfer to the environment. You're making Oklahoma hotter. But you got to pay for that gas that you're burning. You got to pay for the 1303.6. And so here we'll get our we'll get our efficiency now. Here goes. I'm getting 0.5848. Is that what I got when I did this before? Let me look and see. 0.5848. I can't read my own writing. That's the problem. I don't see it here. Yeah, there it is, 0.58. Yeah, that's it, guys. Yay, we did that. Now, did we answer all their questions? Let me go find this problem. We did problem 1058 is what we did. It's an auto cycle. And it says here, find the highest cycle pressure. Well, we did that. The highest pressure is this 7,946 kilopascals. We did that. Mean effective pressure. Engine power output. Well, we got that. The only thing we didn't do was the mean effective pressure. Let me do that. Oh, gee, I only have 1 minute left to do it in. I don't remember if I've shown you guys how to do mean effective pressure. But there's no time like the present. Maybe I can explain it better on during our next session. But engines have something called the mean effective pressure. And what it is, it's the network, in this case, the little W net divided by your change in your specific volume. Now let's see if we can do that. The network is 762.4 kilojoules per kilogram. And the change in volume would be the 0.8126 minus the 0903 cubic meters per kilogram. Okay, I'm going to do that. And we're going to get the mean effective pressure. Here goes. 762.4 divided by 126.0903. Well, I got an answer. I'm getting 1050 rounded off to 6. The units turn out to be kilopascals. See, the kilograms cancel. And a kilojoule is a kilonewton times a meter. So that'll give you a kilopascal. Well, we did that. We answered theirs, and is that what I got? Let me see. Mean effective pressure. Yeah, it'd be nice if I could read my own writing. Ten 1056 kilopascals. Yes, that's what the answer should be. Okay, do we have any last comments or questions? Because I'm going to put this cursor over this little red box here, and I'm going to say adios. And I'll work on that homework that you guys turned in, and I'll put some grades on Blackboard for you, and we'll sort that out. And you have a main thing you got to worry about is that test. You should get busy working on that. You've got till very late Friday night, I think. Well, this is just Wednesday. You got time. Any last words or comments? I'm listening. Here's your chance. 5, 4, 3, 2, 1. Okay, bye-bye for now, students. I'll see you next time.